Hi, everyone. Welcome back to E54. Today, we're going to jump into Lecture 6, Mechanical Behavior. So the general things we're going to do is introduce the class to talking about how we deform different types of materials. We'll talk a lot about these features, stress and strain, and also relationships between them. We'll talk about different types of deformation as well. So elastic is reversible. If you want to think about it like a rubber band, you can stretch it and it comes back. And plastic is permanent deformation. And finally, we'll also talk about some different types of aspects that are more complicated in relating to deformation, things like toughness, ductility, and other features. Okay. And generally, what we want to understand after today is how do materials deform when they're mechanically loaded, what's actually happening inside of them, and then what dictates that load needed to deform a material. And these are just those key words I mentioned. So we'll talk a lot about stress and strain, how they're related, elastic behavior, which is reversible and happens at small loads, plastic behavior, which is permanent, and then toughness and ductility. And I just want to bring up an interesting example from nature before we move on. So nature is actually pretty ingenious. So if you look at your bones, you can see evidence of a material which has evolved and is actually living and sort of redesigns itself based on its usage. So this is a cut through a chunk of your bone. This is your hip joint. This is the bone that goes in your hip. And you can see that it's much denser. It has fewer air pockets here than it does down in this region in the main part of the bone of your femur. And that's because that hip undergoes a lot higher forces. Okay, so it needs to be stronger in this one region compared to the region down here. There's also other interesting things that it actually forms that bone along lines associated with the stress and the strain inside of the sample. There's actually some cool evidence that, for example, in astronauts, where they go up in something like the International Space Station, they're not walking around exercising in gravity. This bone density changes while they're up there. All right, so we're also going to talk a little bit about failure, so how flaws in our material end up leading to failure and how that looks in different classes of materials. And we'll also mention a few examples both today and in our next class about how loading rate and history of loading and temperature affect those important stresses. And just as a few examples, we can find all kinds of places where material or mechanical failure happens. So that hip implant is a good example. Here you get cyclic loading from walking many times. A computer chip experiences not direct loading, but as it heats up and expands and you have different materials contacting each other, it develops stresses and strains. And this happens sort of from going through different thermal cycles. And finally, you can think about a ship experience cyclic loading from so the waves, the environment that it's in. Okay, so first we want to start with the simplest type of deformation, and this is elastic deformation. And really what we're talking about here is we're just stretching the atomic bonds that are holding the atoms together. And in fact, when we think about this, we can build up our understanding by going back to that description we had of the bonding between atoms. So when we drew the bonding energy or even the potential energy of the system, we had this type of shape of how it changed with atomic separation. And we said that our lattice constant was related to where that bottom of that energy well was, right? If we go and we take the derivative of that, what we'll get is what's the bonding force. And we can look at what the slope of that bonding force is around that equilibrium position. And that tells us how hard is it to stretch out a few atoms. If instead of for a single set of atoms, we think about our general material, we could go and take a big block of material, pull on it, and measure the load and the elongation. And this type of behavior is that elastic type of description. Now, normally we don't see load and elongation on these type of plots. We usually try to normalize them to take geometry of the sample out of the equation. And we will talk about things like stress and strain. But this type of straight linear elastic is a common thing to see when we are talking about elastic deformation. And what I'm showing here on this slide is, as we're doing this type of deformation and we think about, first we have our larger sample, we can also zoom in and look at what the atoms are doing. So on the left here is showing the initial shape of your sample. As we apply a force, we'll displace the sample, it'll get longer, the bonds are stretching. And then as I unload the sample and move the other way, the bonds unstretch, atoms get closer together, and it goes back to its original shape, okay? So this elastic term, when we're talking about deformation, really means that the deformation is reversible. Now, what I've shown here is linear elastic. So where that slope of that line is straight, it's a straight line. It doesn't necessarily have to be that way. You can also undergo a process like that, which has this curved shape of the green curve, which is nonlinear elasticity. Most metals and ceramics are linear elastic. Some polymers are linear elastic and some are nonlinear elastic. Now, if you're talking about that nonlinear elastic behavior, it becomes a little bit more complicated to measure your elastic properties. But as you can imagine, if we have that linear elastic, a straight line, we're going to look at the slope of that line. In the same way, you're going to look at the slope at different points on that nonlinear curve. I'm just showing you two examples of how you could potentially do this. You could look at the tangent modulus, so take some line that's tangent to this curve, talk about that slope at any given point. Or you could talk about a secant modulus. So what happens if we take a line that starts at 0, 0 and comes up and intersects this point? Those are two different ways you could describe this curve at different points. Now we can contrast that with what happens when we have permanent or plastic deformation. Again, we're starting with our same sample, we're pulling on it, but rather than stretching those bonds and having them go back, we still do stretch bonds, but we also have some displacement of the atoms. This is actually happening by movement of those dislocations that we mentioned recently in the earlier class. And what happens when you unload the sample is those bonds will become unstretched, but that place where that dislocation moves and that plane sheared doesn't reverse itself. Okay, so the way that looks in our force displacement curve is we have that linear elastic first region. Our curve starts to bend over and it no longer is linear. And then when we unload, we follow the same slope that we did at the beginning back to 0 force. Okay, so we're linear elastic at the beginning, at the end, but there's some elasticity and plasticity happening here. So before we go on any further, what we need to do is define some of these terms I've mentioned in passing: stress and strain. So stress is just a way of normalizing force to remove the geometry of the sample size you're talking about. So we'll start with the simplest one to visualize. This is a tensile stress. So we're taking a pooling on our sample up and down in this case. We're going to take that force that we're applying and we're going to normalize it by the cross-sectional area. And this is just done because you can imagine if I have a very skinny sample and I pool on it and I compare that with a fat and wide sample, it's going to take more force to destroy the wide sample. But fundamentally, that's sort of just the geometry. I don't care about that. I want to think about the material itself. So the tensile stress is that tensile force divided by that cross-sectional area. And the units you'll see on this are sometimes in pound force divided by inches squared. More commonly, we'll use these metric ones, which are newtons per meter squared. Okay, and one thing is that we often have for newtons per meter is the same as a Pascal. Similar to how we defined a tensile stress, we can also define a shear stress. And really what we're talking about is just having a different type of force. So rather than taking and pulling the top and bottom to stretch out that sample, we could take and shift the top and bottom surfaces so that the sample is sheared. So the force is going tangential to that top and bottom surface. But in this case, we're still normalizing that force divided by that cross-sectional area it's acting on, okay? And this is just called a shear stress. Oftentimes you'll see these different symbols used. You'll see a sigma for tensile stress, a tau for shear stress, but sometimes you'll see a sigma for both. And I just want to show you a few different common states of stress that you could run into. And as an example, you can see some of this differentiation between tensile and shear stress in this example taken from a ski lift. So the cable that is coming around the ski lift and holding the chairs is under simple tension. So it's just a wire. It's being held under some force, and we can take the cross-sectional area and think about how much that's deforming. This drive shaft, which is turning to actually make the chairs move around that ski lift, is actually going to experience a shear stress. And we could talk about whether or not that's enough to destroy my material or not. We'll get to that later. Simple compression is a little bit easier to visualize. So in this example of a large rock that's sitting here, this smaller piece right here, we could imagine what's the weight, think about the area it's acting under, and talk about what the stress is there. You also see this same example oftentimes in things like bridges. So in this case, these vertical members on this bridge are going to be under compressive stress. We don't just have to have stress in one direction. It's also possible to have different axes of your sample deformed at the same time. Good example of biaxial tension is a pressure vessel. So it can either be a gas tank or a vacuum tank. And basically in this case, you have a stress in the longitudinal direction and then in that hoop direction, so around the circumference of this cylinder. And you can also have hydrostatic compression. A good example is if you or a fish is underwater, all that water is pressing on you from all directions. And in this case, it's trying to compress you. So the other side of this, if we normalize force, we also need to normalize how much we're displacing our material. And the way we do that is we take that displacement and we divide it by the original length of the sample. So on this picture here, I'm showing in black as my original sample. It has a length L0. I pull on the sample and deform it an amount of this displacement. And I just want to measure that. If I'm pulling on it, I can measure the tensile strain. Another thing you'll notice is if you take and you pull on a sample and stretch it out in one direction, it will get smaller in the other direction. So we can also talk about that lateral strain. So how much does the sample pull in as I stretch it? And we can also define something like this for shear strain. So we do it in a similar way. So in this case, we're talking about how much we've sheared this box, delta X, and we divide it by that Y amount right there. So how tall is that cube and how much have I sheared it over? If I do the geometry of that, you could also describe this in terms of that angle theta through which this box has been sheared, and it would be the tangent to that angle. This slide is just showing a few more examples of what's happening in tension. Again, our original size was this blue dashed cylinder, where as we pull and stretch on it, the sides come in and the material strains laterally as well. And if you flip that around and you think about the opposite, if I take my dashed blue cylinder and I compress it and it gets smaller in the vertical direction, it's going to end up getting wider in that horizontal direction. On the bottom left is a 3D view of that shear strain. And finally, is showing, bottom right is showing a torque. So this is almost what we saw in that drive shaft of that ski lift. So if I were to take a cylinder and just take the top and twist it, I would be applying a torque to my sample. So getting back to that elasticity, if we go and we do apply a tensile stress, and we now, instead of plotting force and displacement, we're plotting stress versus strain, we would still find that this curve is linear. And we're going to actually look a lot at that slope of that linear curve. And we're going to call this our modulus of elasticity. Sometimes you'll hear it called Young's modulus. and we'll use the variable or the letter capital E to represent this. And Hooke's law is an equation expressing what we're showing on this plot right here. It's saying that stress and strain are linearly related, and they're related by this variable, Young's modulus. So just a few important points of order. So in this equation right here, elastic modulus and the stress are going to have the same units because strain is a dimensionless quantity. If you remember when we talked about it, we said that it's the displacement divided by the original length. So that means it's something like meters divided by meters. Okay? So this will be unitless, and these two right here are going to be in the pascals. Okay. Now, often for engineering materials, it's many, many pascals. So we're going to have some qualifier in front of that. For example, a typical elastic modulus is in the gigapascal range. That's 10 to the power of 9 pascals. And applied stress might be typically in the range of megapascals, so 10 to the power of 6 pascals. And just by looking at that, that tells us that strains we apply to materials are usually pretty small. So if we have a number on the left, which is much smaller than that Young's modulus, this strain value has to be pretty small. Now, we can also define other elastic properties besides Young's modulus. I mentioned that idea that as I stretch on a sample, the sides want to pull in the other direction. We can describe that by what's known as the Poisson's ratio, or mu. And mu is just defined as the negative of the strain in the lateral direction divided by the applied tensile strain. Okay. So as I go to the right to positive applied tensile strain, my lateral strain is negative because the sides are coming in. And I just use that negative to make the value be a positive number to simplify my life. So generally for metals, this value is going to be about 1/3. It's a little bit lower generally for ceramics, and it varies quite a bit for polymers, but it can be higher for polymers. Okay. So one important point is we usually talk about this Poisson's ratio during that elastic type of deformation. And these ranges, or these values shown right here, are typical values for the elastic range. If we were to continue our experiment or into the plastic range, what we would actually be getting is a value of Poisson's ratio equals 0.50. So plastic deformation, when that's occurring, we're not changing the volume of our sample. So Poisson's ratio equal to 0.5 means the volume is staying the same. And in contrast, if we have Poisson's ratio higher than that, it means the density is increasing. If we have a Poisson's ratio less than that, it means the density is decreasing. And that could happen if voids were forming inside of your material. So similar to how we had Young's modulus to relate tensile stresses and strains, we can have a similar elastic modulus to relate shear stresses and shear strains. Here we just use a different term, capital G, for that shear modulus, but it's the same type of thing. So it's the slope of this curve of shear stress versus shear strain. It could be something we get out of the torsion test. And we can do this for other types of deformations as well. So another common type of deformation is what's called the bulk modulus. So this is if I apply a uniform pressure to some sample. So for example, put something under water and the pressure of that water is pressing down with it. I can measure the change in volume normalized by the original volume. And here I'm going to use another modulus value, capital K, and I'll call this the bulk modulus. Now, for isotropic materials, where the properties are the same in all directions, only two of these can be independent. So for example, if we have Young's modulus and Poisson's ratio, we can calculate what the shear modulus should be. What I'm showing on this plot is just a way of breaking those stress strain relations through Hooke's law down a little bit more. So if we want to, instead of talking about stress and strain, we want to relate the displacement to the applied force and the elastic properties, we can rephrase that equation in that form. And in this case, the displacement is going to be the force times the original length divided by the modulus times the original area. Okay. And similarly, we can make an equation that describes this type of torsion. So again, this is if I had a wire and I'm twisting it. Again, the material property that comes in is the shear modulus. The properties to describe the geometry are also important. The applied moment is the last thing that we have to add in there. And again, we can manipulate all those things. If I want to, for example, replace and put this in terms of and find what the displacement in the lateral direction is, I can do it. And I will again see my elastic properties. The only thing that happens if I'm talking about pulling in tension, and I want to talk about a lateral displacement, I need to know what that Poisson's ratio is as well. So in these types of deflection equations, what we're getting is a sort of combination of material. So that might be these ones that are colored in this purple color, the geometry of our sample. So that might be the ones that are in red here. And then the loading parameters. So the force that I'm applying or the moment that I'm applying. Now, generally, if I look at all these curves, if I say don't want much displacement, I want this value of displacement or the angle through which this displaces to be low, I would want large values of our elastic moduli, either E or G. So the way we actually do this is shown in this schematic. This is a sort of typical tensile test machine. So if we have a bar of some material, maybe it's some metal you're interested in, what we usually do is we load this up. Oftentimes they have screw type of crossheads that can hold onto that sample. And then we'll basically take and have a moving crosshead come down. And what it does is it needs to continue moving, keep pulling on that sample. So we're really applying a strain to the sample. And what we're measuring up here is what's the load we're putting on some load cell at the top. Okay. So, and once we have that force and displacement and we know the geometry of our sample, we can calculate stress and strain. Sometimes you'll even try to take direct measurements of how much the sample itself is deforming rather than just using the crosshead values. On the right here is just showing a typical tensile type of sample. One thing I want to point out is that usually this region up here by where the sample is held onto or gripped is thicker. And then there's this smaller region, smaller cross section. And the idea there is that you then know where the sample is going to fail. So this is what you would use here. This gauge length would be what you are using for your strain calculations. And maybe the cross-sectional area of that gauge section is what you use for your stress calculations. What I'm showing on this slide here is just a real-world example of that. It's in the horizontal orientation rather than vertical, but this crosshead here is going to move to the right. This left side is going to stay stationary, and there will be a load cell over here. And this piece of copper, we can see it stretch out quite a bit. Now, eventually, when this sample fails here in the middle, we'll see the cross-sectional area reduce down at the very end. This is a process that's called necking. So we're stretching this out quite a bit. You can see that cross-sectional area reduces, and finally, the sample snaps and breaks. Now, again, I just want to remind us that this isn't totally disconnected. How hard it is, from the things we've learned before, how hard it is to sort of stretch and pull that material, or what that elastic modulus is, it depends on the bond strength of the material. So if what I'm showing here are two of those force versus separation curves, where this red one would have a higher slope and would therefore have a higher elastic modulus than this blue one. And we can see that if we look at, for example, two different types of metals. So here, this is showing stress strain curves. At the end, it starts to curve over, but they're sort of just focusing on the linear elastic portion. And you can see, for example, to reach this value of 30,000 PSI, it only takes 0.001 strain for steel, but it takes 3 times that value for aluminum. So that tells us that the bonding in steel is much stronger and the slope of this curve is much higher. So it's going to have a much higher elastic modulus. And this plot is just showing us some of the different values you can see for common different materials. So we were talking about aluminum and steel in that case, and you can see that the modulus elasticity is about 3 times higher for steel compared to aluminum, which matches that graph we saw. But what you can see is even for metals, there's a pretty large range. So magnesium is about 10 times more compliant than tungsten. Right? Now, at the same time, I also want to point out there's not huge variations in Poisson's ratio. So Poisson's ratio is pretty consistently about 1/3 for all these different metals, although it changes a little bit. On this plot, what it's showing is for those different classes of materials we talked about, metals, ceramics, polymers, composites, what are the different ranges of elastic moduli you would expect? So metals and ceramics have the highest elastic moduli, but again, there's quite some spread. So things like tungsten are much higher modulus than things like magnesium. And you can also have variations within the ceramic space. So diamond is very high modulus, which we call stiff, and ice is very low modulus or compliant. Right? Polymers are generally much, much lower than this. So they tend to have really low elastic moduli. And you can see, again, this is a log plot. So these are, every time I go down one of these things, it's a factor of 10, right? Now composites, because they're mixtures of these other types of materials, always fall in between. All right, so let's think a little bit about that permanent or plastic deformation. And I'll give the caveat that right now we're talking about plastic deformation at low temperatures. Now, low is relative, but we can say it's below about 1/3 of the melting point. Okay, so if I look at my simple tension test, I have my stress strain curve. Originally, I have that elastic region where I'm just stretching bonds. If I keep going, I start to see a deviation from that linear elastic. It's important to point out, though, that I'm still having elastic deformation, okay? So there still is some stretching of those bonds as I continue to load my sample, but I'm also getting plastic or permanent deformation. Okay, and this is just, again, showing those individual steps. So one thing we might care about in this type of load that I do, so this loading, you get plasticity, and then we unload back to 0 stress, is there's some residual strain that's left over, or a plastic strain. If you want to think about it, this is the amount that my sample has permanently elongated. Now, a common thing to want to describe is where your material starts to yield. So where it deviates from that elastic behavior and starts to undergo permanent plastic deformation. It turns out to pinpoint that exact point is difficult. So what we usually do is define the yield strength of our material as the stress at which a noticeable plastic strain has occurred. Okay, and a common way of doing this is to apply the value of 0.002 or 0.2% as that value for noticeable strain. Okay? So if I load up and I unload and I have a noticeable strain, I'm going to call that my yield strength of my material. So I want to show you a few different examples. This is another place that virtual material science and engineering comes in handy. So let me exit out of my slides real quick. I'll pull open our Wiley Plus. So if you go to Read, Study, and Practice, Virtual Material Science and Engineering, I'm going to open up the tensile tests. And what I can do here is I can look at different materials and how they deform. So I'm going to start with something That's pretty soft. So cast iron is pretty soft. This is showing how my tensile experiment goes, and eventually it breaks. I can compare that with something like a different type of steel. So just all steels don't deform the same way. There's lots of variation. So in this case, the material is pretty elastic, and then it's strong, and then there's not much hardening. And if I want, I can sort of start to add different options for stress strain curves on there. So sometimes we have plasticity, and then the sample just kind of draws out. Other times, I'm going to reset this. Maybe I'll just close it and reopen it. This aluminum is the one I want to show. So other times we have something that's called strain hardening. So the sample loads up, it starts to yield, maybe something around 300 megapascal. And the stress that I need to apply to continue deforming it keeps rising, and it goes up somewhere around 500 megapascal over time. Now, one thing I can do is I can compare this with softer materials like rubber. So rubber is deforming and stretching and eventually going to break. And you can see that the scale that I'm talking about is very different. So in the strains, these are whole numbers. So 1, remember, means that my sample has doubled in length. So this can come up to 5 times its original length, but the stresses are really low. So here it's only going a little bit, it's in the tens of megapascals. We can compare that with the aluminum. The aluminum is much higher strength, much lower strains. Okay, so that's a helpful tool for getting a feel for what these curves look like and how different materials behave. And we can look at, again, the yield strengths for different sets of or classes of materials. So generally, the order we would go from is ceramics are the strongest, metals are in between, and polymers are the weakest. Okay? But I do have to point out that there's one caveat there. This is true when we're measuring the strength of ceramics in compression. So when we start talking about fracture, we'll talk about how ceramics are very brittle. So if I pull them in tension, they don't survive much. But if I push them in compression, they can survive to very high strengths. So we mentioned that yield strength. So when that sample starts to yield, another quantity we might care about is something called the ultimate tensile strength. And that's the maximum stress that this curve reaches. Okay? If you want to think about it, if I have a part out in some engineering application, if the stress in that sample goes above this, the sample is going to fail. So you can plastically deform and your part can survive, but once you go above that ultimate tensile strength, you can no longer survive. Okay? And after this point in metals, this is when visible necking starts to occur. And in polymers, you can also get necking, but this is where the polymer chains start to align and break. All right, so let's sort of test our understanding real quickly and ask ourselves which one of these points would be the yield strength of our material. All right, let's go through the ones it isn't. So we just mentioned that the highest stress that our sample can hold is the ultimate tensile stress. Okay, so that's not it. This final point is where the sample breaks. That's not it. We're talking yield stress is the original place that we have plastic deformation. A is pointing to when there's 0 stress and 0 strain on the sample. That's not it. B and C are reasonable places you could start. So B looks like it's trying to find the first time it's not linear. But remember, we said that yield stress is defined at some noticeable strain. So this is going down to that 0.02% offset. So the answer is going to be C in this case. That's our yield strength of our material. In this case, it's a little bit below 300. Maybe it's 290 megapascals. All right, what about the ultimate tensile strength? Well, I gave you the answer. We talked about it. It's the highest stress that our sample can hold, so it's going to be D. So we mentioned that point at where the samples fail. We can also want to quantify that, and that's something that's called the ductility of the material. So it's how much I can stretch my material before it fails. There's a few ways you can describe that ductility. You're basically saying how much can I deform my sample. One way is through what's called the percent elongation, okay? So that's just saying I'm gonna take the final length of my sample, subtract from it the original length. So it's saying how much the length has changed, and I'm gonna normalize that by the original length of the sample, okay? And oftentimes we express it as a percentage. You can do a similar calculation if you look at how that cross-sectional area changes. I showed you that example of a copper piece getting pulled, and I showed you how the cross-sectional area reduced at the end. You could look and take a similar measurement by looking at that cross-sectional area, that percent reduction. Now, generally, here's showing two different materials, one with a low ductility and one with a high ductility. Okay, so the blue curve is pretty strong, but not very ductile. The green curve is moderately strong, but then it has a large percent elongation. And again, just reminding you can have that other measurement. So toughness is a term that can be used in several ways. In the most general meaning, what its toughness is talking about is it's the amount of energy a material absorbs before it fractures. So if I think about it, how much energy do I have to put in to take the sample, pull it until it breaks and can no longer put back together? So specimen geometry is going to play an important role in that. And more common than toughness, we're going to talk about fracture toughness, which tells us that if we have cracks in our material, how hard is it for those to grow? Okay? And we'll talk about that in a later class. But it turns out that the reason we do that is almost all real materials are imperfect. They might have some cracks just based on how we make them. So we need to think about how those grow and fail. For now, while we're talking about our tensile tests, we can think about the toughness or the energy needed to go and break our material and recognize that it would just be the area underneath the stress and strain curve. So if I take those examples of a few different types of materials, that blue one I showed might be what a ceramic looks like under a tensile stress. So very little ductility. A metal might be moderate strength and I can pull it a lot. And then something like a polymer might be low strength, but I can really deform the heck out of it. If the toughness is that area underneath the curve, what you can see here is in these different sort of representative examples, the metal actually has the largest toughness, okay? And that's a general thing we can say is that materials which have high strength and high ductility are what we want for a large toughness. The last point on this is that this fracture point can either be brittle, which means it's just elastic energy going into it. So that's usually what we see for a ceramic under tension, or it can be ductile. So for a metal, we're having both elasticity and plasticity going into the system before we break it and fracture it. A concept that's related to toughness is something called resilience. This is saying how much energy can I absorb just from elastic deformation, okay? And this is basically talking about what's that area under the curve just in the elastic regime, so before the yield strength of the material, okay? A way you can actually see this is if you take a rubber band and you elastically deform it over and over, and then you go and touch it, you'll notice that it ends up being a little bit hot, okay? And that's telling you that even though you have reversible deformation, you're doing some work on the system. So if you want to do a simple calculation of what the resilience of your material is, and if you assume linear elastic behavior, you can go and say that your resilience is going to be 1/2 your yield strength divided by your yield strain. Now, we don't usually measure yield strain, so what we can do is reorganize this using Hooke's law and say that our resilience of our material is generally the yield strength squared divided by 2 times the Young's modulus, okay? So this amount of stored strain energy ends up being very strongly dependent on the yield strength of our material, okay? And this concept is also going to pop up when we talk about fracture as well. So first, I want to just redraw this elastic strain recovery type of mechanism. So here we're loading up, we're linear elastic, we hit our yield strength of our material, we have that combination of elasticity and plasticity. We unload, and we talked it before about that, how that residual strain that residual strain that remains is our plastic strain. We could also think about how much strain we've recovered during this unloading process. So our total applied strain was here. We recover some amount, and then we have some amount left over. Okay. Now, if we reapply the load from the bottom of this region, we're going to again follow an elastic curve, and we'll come back along this linear elastic range up until that point where the load started to decrease before, and then we can continue to plastically deform our sample. All right, let's do a sort of sanity check and make sure we understand these terms. I'm gonna ask you, which of the following material properties characterizes a resistance to plastic deformation? So let's go through them one by one. So ductility is how far I can stretch my material before it breaks. But I mentioned that something like rubber can be really, really easy to stretch out, but I can stretch it a lot. So ductility doesn't work. Toughness, this tells me how much energy I put in before I break. But again, that's talking about that point at which it breaks, right? Resilience, how much energy I can put in during elastic deformation. Well, that's not directly measuring our resistance to plastic deformation. Yield strength, what's the stress I have to apply before my sample starts to plastically deform? Okay, part D is the most direct property that describes the resistance to plastic deformation. We talked about stress and strain, but in most of those definitions we were using, we were saying the stress is the force divided by the original cross-sectional area, but we also acknowledged that that cross-sectional area can change as I pool on a sample. So we need to introduce the concept of what's called true stress and strain. So those metrics we used before, stress is force divided by the original area, and strain is the elongation divided by the original length. Those are what's called engineering stresses and engineering strains. Okay? We can also describe what the true stress is. So that would be the force at a given time divided by the area at that given time. Okay? And that area doesn't have to be equal to the original area. Similarly, we can do this with our strains and talk about it being the strain instantaneously divided by the length instantaneously divided by the length at time immediately before that, and we represent that with a natural log in this case. Okay. The reason we don't directly calculate these are often these things are hard to measure during a test. So it's hard to know exactly what the cross-sectional area is during a test, but it's easy to measure your sample before you put it in. What this plot on the right is showing you is this bottom curve is the engineering stress strain curve. There's elasticity here, but it's really small elastic strains before the sample starts to plastically deform. So we're seeing mostly the plasticity. And this curve right here, this engineering stress and strain, if we were to convert this to true stress and strain, the curve would actually look like this. Okay? And one thing that tells us is that ultimate tensile strength from the engineering stress strain curve, we said that's related to necking. If we really kept track of that neck, we would see that it still gets harder and harder to deform that necked material, but it's reducing faster than we can increase that stress. Okay? I just want you to be aware of, you can talk about engineering, where we use our original length and cross-sectional area of the sample, or the true stress and true strain, which are instantaneous measurements. This is just showing another plot. If during straining we have no volume change, that means the plastic strain is dominating. We can come up with some nice equations to estimate what the true stress and strain are. So the true stress is going to be the engineering stress times 1 plus our strain. And the the true strain is going to be the natural log of 1 plus the strain. Okay. And again, this is just showing the blue curve is our engineering stress strain curve, and the red is our true stress strain curve. They only start to deviate after we've heavily deformed our sample with plastic deformation. So the other thing I mentioned when we talked about that example of an aluminum alloy with the virtual material science and engineering module is the concept of hardening. So how the strength or the sort of stress needed to keep deforming my sample could increase over time. In this case, it's showing two examples. The blue curve has very small hardening, and the reddish orange curve has a large strain hardening. This increase in this curve can often be described with a relation like this. So this is saying the true stress on my sample is going to follow some power law. So this curve right here looks like a power law, where there's some constant in front of the power law, the strain to some value n. So the higher that value n, the more hardening that curve will have. So it'll go higher as I keep applying strain. And this is just showing some examples. So for example, this number given for copper is higher than that value given for steel. So this is just fitting to the part of the curve past yielding. Finally, so we talked mainly about uniaxial tensile tests so far. There's another type of experiment you can do called a hardness test. And this is something where rather than make a whole sample and break and deform the whole thing, what you can do is come and press some probe into the surface of your material with a known force, remove it, and then look at how large of an indent you made on that surface. Okay. And generally, if you did this experiment and you were to measure a smaller indent in your surface, that tells you that it's resisting you pressing on it with the force, and it has a higher hardness. Okay. And you can go and create a sort of scheme to show you how hardness relates to some materials we know and love. So diamond is very hard. It's hard to deform and poke at. But on the other range of this, something like plastic is very easily to deform if I were to push on the surface. So it would have a low hardness. There's lots of different ways you can go and do this type of test. So that example of pressing some sphere of a known shape into the surface is actually called a Brinell hardness test. And if you know what the applied load is and you know the dimensions of your indenter, you can go and calculate what your hardness number is. You can have sharp indenters of different shapes and sizes. The details of this aren't all that important, but the basic idea is you can just make sharp indenter tips of different shapes and go and measure this. And if you do it on different materials, rank them by their hardness. One of the last things I want to mention here is that we often don't want to push our materials to their absolute limit. We want to remember that we often will have design or safety factors built into our engineering. And one way to think of this is that if I know the yield strength of my material, I know when it permanently deforms, I might design my system so that the working strength, the strength I expect it to experience, is some fraction of that yield strength, okay? And this is just giving some ideas of maybe n is between 1.2 and 4. So you can imagine 1.2 means that I'm not that far below my yield strength, whereas 4 means I'm only at a quarter of the yield strength. Okay? So it depends on maybe something like how critical is a failure. Okay, so if you're in a plane and if your part fails, the plane falls out of the sky and many people die, you might have a large safety factor. If, on the other hand, you have some component in some dairy factory, and if the component fails, you break a glass of milk, but you can fix it, maybe you choose a more ambitious safety factor. Okay? And this is just showing an example. You could be asked a question like, if you're given a material, a certain carbon steel, you know how it's loaded. So it's loaded with a certain force. calculate the diameter that you would need to make this part out of so that it would survive with a safety factor of 5. Okay? So all that this did was, in this case, N is your safety factor, so that's given in the problem. The yield strength comes from the choice of material. And then you could figure out what the stress is on this sample. The force is given, and then the diameter of that sample is sort of the design criterion. We could solve for the diameter that would be needed for this. In this case, if we plug in numbers, it would need to be 6.7 centimeters. Okay, so just to summarize, so stress and strain are really size independent measures of load and displacement. So conceptually they're the same, but they're trying to remove the impact of sample size. Elastic behavior is reversible deformation and oftentimes has a linear relationship, but remember that not always, especially for polymers. And if you, for example, wanted to minimize deformation, you would want to select a material with a large elastic modulus. So either Young's modulus or a shear modulus that's large. Plastic deformation is permanent deformation, which occurs when we exceed the yield strength of the material. And of course, if you want to avoid this, you want to choose a material with a very high yield strength. Toughness is the energy needed to break unit volume of material, and ductility is that plastic strain at failure. Toughness is again how much energy we absorb. Generally, high toughness materials are ductile, so we want that plasticity to be happening in absorbing energy. Low toughness materials are brittle. And just to sort of give you an example of material classes, so metals tend to be ductile with high toughness, while ceramics tend to be brittle with low toughness. Resilience is the same type of idea of absorbing energy, but this is prior to plastic deformation rather than prior to failure. And then hardness is some sort of measure of the local resistance to poking and scratching at the surface. All right, so with that, we're at the end of our lecture today. I will see you in a Q&A session, and good luck.